Good afternoon, everyone. It's great to see everybody here today. I'd like to kick off our webinar today by reminding us all of our panel's charge and our mission. So as the Process Studies and Model Improvement Panel, our goal is to reduce uncertainties in general circulation models used for climate variability prediction and climate change predictions through an improved understanding and representation of the processes that are governing climate and its variations. In making progress on this mission, we review, prioritize, and coordinate U.S. scientific plans for programmatic support of relevant process studies and interactions with our supporting agencies. And as part of this, we have this process studies webinar series that allows us to hear from and interact with important activities and process studies that are ongoing. Today, we're here from Armin Sorooshian, who is the PI for Activate. And Activate, I definitely had to write this down to remember what it all stood for. Aerosol Cloud Meteorology Interactions over the Western Atlantic experiment. So Activate was selected 2 years ago, and it will continue through 2023. It's a part of NASA's EVS, or Earth Venture Suborbital program, that not all of them, but several of the funded projects, which include Activate, have a $30 million budget, and this is meant to provide a specific mechanism. This EVS program is meant to provide a specific mechanism for PI-led field investigations that really require a longer-term, systematic, or more statistical approach to get at the science that is proposed, and it's specifically kind of different from what you might expect to see from a single kind of intense field campaign. So the things that are funded in this avenue are a little bit slightly different, and generally, as Armin will talk about, involve multiple field experiments, multiple field experiments. Armin is a professor at University of Arizona, where he's been since 2009. He holds many appointments, which include, and I got this list off the website, so I hope it's correct, but Professor of Chemical and Environmental Engineering, Professor of Global Change Graduate Interdisciplinary Program, Professor of Hydrology and Atmospheric Sciences, Professor of Public Health, Professor of Optical Sciences, and University Distinguished Scholar in Chemical and Environmental Engineering. Armin has his BS, Bachelor of Science from University of Arizona, and Master's and PhD from Caltech, all in chemical engineering. He has many honors, including receiving the AGU Atmospheric Science Ascent Award in 2009. Armin's research is focused on links between aerosol clouds and chemistry, and he has lots of experience in different field campaigns, including CampX, McCall's, FACE, BOAS, Seekers, NICE, DC3, etc. I probably didn't say all those acronyms correctly, but with that, I'll stop talking and let Armin share with us what he's learning from Activate.
Well, first, I want to thank you all for inviting me to present about the NASA Activate mission. It's a great opportunity for us. I'm representing a pretty large science team, and these logos on the far left include the institutions who are original members of the proposal, with maybe one or two exceptions of groups that have been added. So we have a pretty large team, and as you can see from the picture, we're really interested in clouds, specifically the interactions between particles and clouds in meteorology. And so with that, I'm going to tell you what the outline will be for my 30 minutes. I will begin with what the motivation was for how Activate even came to be. Then I'll talk about Activate's concept of operations and our science objectives. Then I'll get into the flight details. What is our strategy of flying? What are the aircraft and instruments involved? I'll give you a status update of where we're at today in terms of how many flights we've executed and other types of details. The second half of the talk, I'll get more into the modeling and analysis and what the different groups are working on analysis, what the different models are, and I'll show you just a sneak peek of early results from each of the different modeling and analysis groups. And I was also asked to comment on programmatic insights in terms of successes and challenges that we've had, so I'll finish with that. So I'm not going to spend a lot of time on this very busy slide, but I think this audience, I'm guessing, is well aware that aerosol cloud interactions are linked to the largest uncertainty in estimates of total anthropogenic radiative forcing. So it's a very important topic to keep investigating. And really, this little box here is important. Why is there such high uncertainty? Well, it's a very difficult topic to study. You can't bring clouds down into a lab. It's hard to get into the clouds and build statistics. And the reason we need lots of statistics is that clouds are complicated, and it's very difficult to disentangle the effects of aerosol and meteorology on clouds. All of it's connected. So really, we need lots of statistics in different conditions to make advances, and that's what Activate's all about. So now I want to sort of tell you the motivation for how this mission came to be, and quite a bit of it is just based on a lot of my own personal experiences in past campaigns dating back to 2004, my first campaign with this plane, the Surpass Twin Otter. Most of my missions have been with this plane, funded by the Office of Naval Research. And a lot of the campaigns I've been involved with go off the coast of California, which is an excellent natural laboratory to study aerosol cloud interactions because there's persistent stratocumulus clouds in the summertime that are low, they're very accessible, and there's lots of ships that create a strong perturbation of aerosol, which is what we need in this field of study. So typical flight we do out there, we do these types of modules as shown in this animation, where we do a level leg below cloud, different level legs in cloud at different altitudes, and then pop up and do maybe one or two more level legs above a cloud. And then we do spiral soundings on the sides of the clouds. And each time we do this type of module, it takes well over an hour. Okay, so we've learned a lot by doing these types of flights, but there's been a lot of limitations. For one thing, the plane is not very large, so you can't fit a lot of instruments to measure everything you'd want to help understand the complicated aerosol cloud system. And by the time you maybe reach this top leg, what you're sampling may not necessarily be representative of what's going on below that leg in the column. And also, as Patrick beautifully said, lots of campaigns just go to a region and focus on intensive operations just for a few weeks. And it's very hard for everything to work at the same time in terms of instruments. And also, you don't get a lot of variation in terms of things that change by season. So often we cannot study different cloud types in a one focused campaign. So this is just an illustration of the complexity of the types of processes we're interested in that so-called aerosol cloud system. You know, there's aerosols below cloud, above cloud, and they're interacting in different ways with the cloud system. And you can imagine that, you know, a satellite or remote sensor that's providing snapshots will have a very hard time unraveling the details of each of these processes that we'd like to parameterize well and model. And also a single plane struggles to capture all of these things at once. So again, we need statistics, lots and lots of statistics, and maybe new ways to approach these aircraft field campaigns. So that is the motivation for the concept behind Activate, which is to have now two airplanes, as illustrated in this figure on the top left, that will fly in a coordinated and systematic way, such that the Falcon, shown down here, flies in the boundary layer, sampling the clouds with in situ measurements, and then the King Air flies aloft, looking down with remote sensors, launching dropsondes, getting more aerosol and cloud and meteorological data. So at once, we're really trying to characterize the same column at one, that's relevant for the aerosol cloud system. So that's, and I'll talk a little bit more about the flight strategy in a few slides. So this is sort of the makeup of our team in the bottom left. John Hare is a very experienced project scientist at NASA Langley, and these are the partnering institutions to date. As I'll get to at the end of the talk, we'd love to expand this list. Right now, we have over 120 participants on the science team. On the top right, really the main science goal, one of our key goals is to really build an unprecedented data set that can be used for years, if not decades to come, to improve models and also assess and remove remote sensing algorithms and technologies. So in the bottom right, some more details. Our two platforms, again, are the Falcon and the King Air. The goal that we set out at the beginning of Activate was 150 total joint flights with these two planes. And the study region is the Western North Atlantic Ocean. So we're based out of NASA Langley in Hampton, Virginia. And that was specifically done for a few reasons, one of which is these large campaigns that might go set up shop in another continent, another area. There's a lot of resources lost just for those travel expenses and logistical considerations. So if we base out of where our operations team lives and where the planes normally are, that saves resources to increase the number of flights we can do. And this is so important for Activate because, again, we're driven by statistics. So we want to save all of our resources to just keep doing more and more flights to really build that unprecedented data set. So that's one of the key reasons why we are studying the Western North Atlantic Ocean, to be able to maximize the number of flights we do. But the region also provides a lot of great characteristics for us. To study aerosol cloud interactions, well, it helps to have a range of aerosol conditions as it relates to the types of aerosol, as are illustrated in this top left cartoon. We've got all kinds of aerosol types impacting our flight domain, and also just different levels of aerosol concentration. And that's illustrated in the bottom left. These are spatial maps of what's called aerosol optical depth. So red colors denote more pollution in the column. And I'm showing two maps because this shows the two seasons we are flying. We wanted to fly in February and March, which is sort of the winter season, and then May and June, which is our summer season. So we're getting seasonal factors included in our data set. And this leads to different pollution levels, different pollution types, and also different meteorological conditions. So on the top right, these are normalized PDFs of two pretty important environmental parameters. One is the lower tropospheric stability. And what I'm doing is comparing the Activate region to off the coast of California, where there's been many field campaigns studying aerosol cloud interactions. And you can see very different behavior. We have more unstable conditions off the East Coast, which gives rise to different types of clouds and conditions that we can build statistics around. And on the far right is something called cloud liquid water paths. So we have the thin clouds and also puffier, more juicy clouds. And another important feature of the East Coast is these colder outbreaks that a lot of our team's very interested in. These give rise to shallow cumulus clouds, which models are notorious in terms of being able to simulate well. They typically underrepresent the amount of shallow clouds. So we are building a data set that can be used to improve how models treat the cloud development in these colder outbreaks. These are our three key science objectives. The first one is understanding relationships between aerosol particles, the seeds of cloud droplets, which are referred to as cloud condensation nuclei, and cloud droplets. So we're studying the relationships between those three, and we ultimately want to reduce the uncertainties in how models treat these processes, most important of which is the cloud droplet activation process. Objective 2 is looking at process level understanding of how models treat cloud micro and macro physical properties and how they couple to how clouds affect aerosols. There's often so much attention given to how aerosol particles affect clouds and not so much given to how clouds themselves impact aerosols. So we're trying to look at both sides of the street here and how they interact with one another. And our third objective is assessing and trying to improve remote sensing capabilities for future missions to study aerosols and clouds. And this is very important for example, the NASA ACCP orbital mission. So this is a more detailed schematic now of the flight strategy, just to repeat what I've already said, but a little better here. So the Falcon, again, is our boundary layer aircraft. It flies at low altitudes and it gets all the in situ data we want in and around the cloud. So we do level legs below the cloud, right above the cloud base. We do profiles up to the top of the cloud, and we kind of repeat this process over and over and over. At the same time, the King Air, which is coordinated, and we try to keep it within 10 minutes of flight to the Falcon in the same horizontal band as us. It's looking down with the remote sensors, a LiDAR and a polarimeter, which I'll get to, and it's launching drop zones to get the vertical profiles of weather parameters. And we call this type of module, that's shown here, that usually covers about 100 kilometers of flight, a cloud ensemble. And one way in Activate that we're assessing our success is how many joint cloud ensembles we do with the two planes together. And so we count these, how many we do each flight, each mission, and we have a target goal of how many we want to hit to consider ourselves as being successful. This is a picture of the two planes, the King Air on the top, the Falcon on the bottom. Key details are our flights are typically 3.5 to 4 hours long. And also the airspeeds are such that we can keep them somewhat coordinated. This was an important detail that we needed for Activate to be successful. And of course, there's big wind differentials, like there's a flight going on right now as we speak, where the King Air is flying at an area with much faster speeds than in the boundary layer. So we go through great lengths to try to keep these two planes as coordinated as possible. Sometimes, one of the planes has to do a delay loop and come back to catch up with the other plane. This is a picture of some of the probes on the outside of the Falcon, which is the lower plane flying in the boundary layer. We've got various probes on the top manifold of the plane for sampling things like gases, aerosols, cloud water, and cloud droplets. On the wings, we have different probes looking at cloud and raindrop size distributions. This is the interior of the Falcon, lots of instruments getting the in situ data for aerosol composition, optical properties, hygroscopic properties, gases, CCN, and so forth. This is the King Air, fewer instruments, but larger and more heavy instruments. So we've got the HSRL2 LiDAR and the research scanning polarimeter. And one of the things that the Decadal survey really made a point was to try to have these two instruments combined on a single platform, which is something we're doing. There's a lot of great information that can be learned from the two of them together as compared to the sum of each by themselves. And then, of course, we've got the dropsondes on the King Air being launched. So now I'll talk about just where we're at in terms of our flight status before I get to the modeling part of the talk. So we've, in our first year of flights, which was 2020, we did 40 total flights, 35 of which were joint. So that means on 5 of those flights, the King Air had a maintenance issue that needed to be addressed. So our goal each year is 50 flights. And so you might ask the question why we only hit 40. Well, you don't need me to tell you we had a major event that occurred in March that slowed down life. That was COVID. So we were lucky to get as many flights as we actually did. We were able to pick up things in the summer in a safe manner, mostly because everyone was still based at Langley, so we could still do flights that summer. In this past winter campaign, we had to extend it from February, March to now January, April, because we have to now make up flights that we've lost out on. So we were able to rattle off 21 flights, 15 of which were joint. So again, on 6 of those flights, there was a maintenance issue to be addressed on one or both of the planes. This is a map of the flight tracks in 2020. So these are just out and back flights. We take off from Langley, we go out for an hour and a half, 2 hours, and then we come back. And some days we do 2 flights. So we come back, fuel, and then go back out. We had plans originally to have secondary bases, most important of which is Bermuda. But again, due to COVID, those plans have been shut down. And we're optimistic maybe in our last year of flights, which is 2022, we might be able to go that far. And that will be great for our data set because we get to extend our spatial range and capture new phenomena maybe out there closer to Bermuda where it's maybe cleaner. So in our flights, we've done some underflights of satellites, which is important for the remote sensing aspects of our project, which is Objective 3. We've done 3 underflights for Aster, which is important data to look at cloud morphological properties. We've done 6 underflights of Calypso, which is really important for aerosol retrievals. Down here, I just show you an example of one particular day where we did back-to-back flights. This is in a cold air outbreak, which is marked by these characteristic cloud streaks that you see here. So in the morning flight, just as an example, the red trace is the King Air, the high flyer. So we fly out to an area of interest and the King Air did a big circle launching dropsondes. So we got about 11 around the periphery. And those data are really important for evaluating things like divergence, surface fluxes, and I'll get to in a few slides why this is so important for the modeling teams. The Falcon, in the meanwhile, is within that circle doing stacked level legs, studying the boundary layer cloud system. So together, these data, we can do a lot with it. And so after that, the planes go home, fuel at Langley, and then fly back to the bullseye of that circle, and then go with the boundary layer winds in a coordinated fashion to study the evolution of that air mass that we sampled so well in the morning. So this is what we call a so-called process study flight, where we did 2 flights on the same day, trying to get sort of a Lagrangian perspective of how an air mass evolved. And this is just one example of how the joint plane philosophy is such a good one. This is a nice demonstration of how we can learn more this way. So one of the observations last winter, and we're still making these observations this year too, is that there's enhanced aerosol depolarization ratios in the marine boundary layer as measured by the HSRL2 on the King Air. So if you look at this nice little map here, these green and red colors indicate high aerosol dipole ratios. This is really odd. This parameter, if you're not familiar with it, if the value is high, and if it's a red or green color, that indicates that there's non-spherical particles present, which is really odd because this is usually related to dust, and we don't expect a lot of dust in the bottom of the marine boundary layer. It's typically, sea salt, which is very hygroscopic, which means it becomes spherical if there's any moisture around. And it's typically humid in the marine boundary layer. But what we learned with the lower plane is, with a diode laser hygrometer, a nice instrument that measures accurately relative humidity, it was very dry on these days that we saw this phenomenon. And this is typical of colder outbreaks. You've got these dry conditions in the boundary layer, which means that the sea salt particles were below their so-called deliquescence point. It's a fancy word. That means if you're above it, they can take up water and become a sphere. So if you're below it, sea salt assumes its native shape, which is more of a cubic shape. It's not spherical. So, and also with the Falcon, we can do measurements of size distributions to confirm indeed that, we probably have sea salt, and we have chemical measurements also to confirm that. So this has major implications for, like calliope and aerosol remote sensing. So there could be a lot of aerosol mistyping that has occurred in past data that have been archived. So Rich Farrar from Langley is really leading this work. So now I'm going to transition to the second half of the talk, addressing more of the modeling and analysis efforts in Activate. These efforts are for a variety of things, flight planning and guidance, post-flight analysis, testing, improving parameterizations, and so forth. So here's a list of models and different groups involved. We've got FlexPart, which is a really nice particle dispersion model. We've got the state-of-the-art chemical transport model called GeosChem. We've got Dharma and WRF that can be run in large eddy simulation mode, and WRF can be run in cloud resolving mode. Hailong's more of the expert on that topic. And then we have global climate models like the GIS E3 model, the DOE E3SM model, the NCAR CAM5 model. We also have GEOS5. So we're using models of varying scales, and we're trying to connect them together eventually using this complex web of arrows. This is sort of our idea of how things will relate to each other in terms of data we collect, each model, and what objectives they address from those 3 objectives I've shown before. So we can come back to this if there's any interest later. So now what I'm going to do is just show you a sneak peek of just a slide or 2 from each of our modeling groups. I thought this could be of interest just to give you a flavor of what's been happening. Again, we're only in we finished the 2nd year of our lifetime, which is 5 years. It may actually be extended to a 6th year due to COVID. So really a lot of the key modeling and analysis we want to do is best done when we have the full data set in hand, because again, we are driven by statistics. So at the time, we've been mostly focusing more on case studies, and we're still learning a lot from that. So from University of Miami, Paquita Zaidama and her postdoc Sitala, they've been really interested in the Gulf Stream and the warm sea surface temperatures and what the impacts are on evolution of clouds, especially during periods after atmospheric cold fronts. Again, this is related to those colder outbreaks that our project is so interested in. So they're driven by these 2 science questions here that you can read. To initialize and drive model simulations, typically we rely on these coarse scale reanalysis products for things like fluxes. So the question was, how well can two of these reanalyses, ERA5 and MERA2, how well do these parameters compare to our actual measurements from dropsondes from the aircraft data set? And so we're testing those two and also this OA flux product. And so the punchline of it all, and by the way, on this map, these little circles indicate, individual dropsondes that were launched during our winter campaign in 2020. So the punchlines are that, the reanalyses to first order are pretty darn good in capturing fluxes and, like the wintertime boundary layer height. There's a little bit of a discrepancy in the summertime, which has been documented before, but to first order, they have learned that, these reanalysis data are pretty good in terms of getting boundary layer properties and fluxes. So this is work they have been reviewing at GRL. The GIS modeling group has been running their Dharma LES and Lagrangian model, and they're really motivated by the science question of how do frozen hydrometeors impact the transition from these overcast cloud decks into more open cloud fields. And again, this is characteristic of what we see during colder outbreak events. And this transition is really important to understand because, of course, it has important effects on radiative budgets. So what they've learned from their simulations is that, let me just go to the next slide so you can see a bunch of different curves on the far right, but it's pretty complicated. But the punchline here is that rain, the initiation of rain is very important for this transition to occur, and any simulation they ran without any aerosol loss did not lead to this sustained cloud breakup. You need aerosol loss. And in gray, they shaded a period of time, which they call preconditioning by riming, where ice, these frozen hydrometeors are doing various things to get the system ready to begin this process of rain to lead to that cloud breakup. So this is work that a postdoc at GIS, Florian Tourneau, has been leading, and it's in review at ACPD. Hailong's group at PNNL has been running WRF in the LES mode, also to try to understand these aerosol cloud interactions in these colder outbreak marine boundary layers. And so one of the important findings that they've come up with, this is also a paper in review right now, is that the Activate data compare pretty well again with these reanalysis data in terms of the types of properties we need to initialize and drive these sophisticated LES models. Okay, and they've been doing a lot of integration of field data into their modeling analyses. And the fact that they've confirmed that these reanalysis data compare well to the aircraft dropsonde data, for instance, now we can answer these important science questions down here with WRF, driven by in this cloud resolving model mode. So down here, there's a couple important questions that they're currently working on. These figures just show how nicely the LES can capture these mesoscale cloud morphological patterns that we see in the GO16 imagery. So this gives us really good confidence in these WRF simulation results that are driven by reanalysis data and our aircraft data. Now, Alison McComsky at Brookhaven National Lab and her postdoc Minnie have been working on some really interesting analyses of decadal trends in what they call surface downwelling shortwave radiation. And what they've seen over the Western North Atlantic Ocean over time is increased brightening. So that, again, there's more solar radiation reaching the surface. And this has been confirmed from satellite and reanalysis data. And so they're working with David Panamal at Langley to understand what are the factors driving this increasing brightening over time. So they've looked at things like aerosol. So there's been a reduction in aerosol over time. That's been pretty well documented. There's varying patterns in cloud fraction, but there's been a pretty strong reduction in cloud optical depth that matches where most of the brightening has occurred. So this is, again, work in progress. Zhubin Zhang at University of Arizona, a colleague of mine here, he's been working with this group with the CAM model, evaluating the club turbulence parameterization. So they've been comparing our aircraft data for turbulence to club. And what they see is that the club turbulence is weaker than what we've observed in the field. This has ripple effects on, the cloud droplet activation process. So weaker turbulence means you get less cloud droplets being condensed. And they've done some analysis to sort of show this by comparing our field data to the CAM data. So they've been really focused on turbulence thus far. Hongyu Liu at Langley, he's been really instrumental in our forecasting and flight planning activities using GEOS 5. So he's providing all these various products to us. Literally right now, there's a weather meeting that I'm not attending, but they're showing these types of figures for planning on tomorrow's flight. So we have speciated AODs, which is really important to know, like if there's smoke or dust, some target of opportunity we want to go after in the next day's flight. They've also done some really nice analysis looking at transport patterns of pollution that are impacting our flight domain. Of course, the boundary layer outflow of North American pollution is very important behind cold fronts. So that's been a big topic of interest thus far with our Activate data. So more broadly, my group's also been involved with analyses, and we've got a website here that's got a list of our 20 or so publications to date. These 4 are quite important. I think they provide a lot of context for anyone who's interested in using our data at any point in the future. This BAMS paper introduces the campaign and the strategy. So basically goes over the first 15 minutes of my talk in a little better detail. We did a review paper to summarize all atmospheric research that has occurred over the Western North Atlantic Ocean, dating back to the 1940s or so. So that's a wonderful resource. And then we have a part 1 and 2 paper just published in JGR looking at new data, reanalysis data, observational data, satellite data. Part 1 is focused on chemistry. Part 2 is more focused on clouds, precip, atmospheric circulation, and things like that. I'm going to close now with a couple slides talking about the programmatic insights now of what have been the project's, some of the important successes and challenges. And I'll begin with successes. At least from my perspective, the job's been much easier than I thought it would be because we have such an experienced team, which has really helped, especially John Hare, who's our project scientist, our deputy project scientist, Rich Farrar. These 2 have been involved with the campaigns for a very long time. So they've been really helpful in knowing how to do certain things. Our project manager, Mary Kleb's, also been involved with many of these large-scale missions, which has made planning and all kinds of things easier. We have a very strong forecasting team comprised of Michael Shook and Amy Jo Scarino at Langley, which has made flight planning very easy and very successful. Our flight scientists on both planes are really good at getting their heads out of the instruments and out to the atmosphere to help make real-time decisions about how to do audibles to help optimize our data quality. So they've been really excellent. All the instrument teams generally in Activate have a lot of experience with these campaigns, and they've worked together a ton. So that's helped make smooth operations. We have a lot of different modeling and analysis groups who each have been active using our flight data thus far. So that's been really helpful, and they're putting out papers and review and presenting at meetings. Now with COVID, when that hit, most projects of this nature had to be shut down. There were not a lot of field campaigns that have been executed since COVID, but because we were based, all of our operations people at Langley, they live pretty close to there, we were able to still fly after some time, in the summer, which really helped our project out in terms of keeping up with our flight goals. And the fact that we had 2 small planes also helped. That helped with, some of the social distancing. If we're on a DC-8 that requires a lot of people on a plane, it would be much harder to social distance. So having 2 little planes actually has paid dividends. And in general, having these 2 planes flying in a coordinated way, I think we're demonstrating it's very successful and might be a consideration for future missions that have wallets sufficiently deep to support that type of effort, because it's not cheap. Challenges. Obviously, COVID has had a challenge. Even though we've been somewhat successful still flying, it's put a dent in our plans. We're not flying as much as we wanted to. Having meetings, as you all know, is very difficult if you cannot see each other. This is a big deal in flight planning when you have to make very difficult decisions. Not being able to see people makes it a lot more challenging. Usual aircraft issues have haunted us, but we're still adapting to these problems that seem to come up every now and then. The modeling teams they're all doing sort of more of their own thing right now. Thankfully, they're integrating aircraft data, but working together, I think that takes some time to bring the modeling teams together to work on sort of a unified topic. We're trying to work on that. It just takes time. We, as a project, want to have an open data workshop in October as part of our next science team meeting. The idea is to recruit people from outside our main team to get excited and interested in our data to hopefully use it for their research. And so that's one of the questions I was maybe thinking of asking this panel in our discussion. What advice maybe do you have from your experience how to recruit such an external audience? We can send the normal emails and give talks, but maybe there's other strategies that you can recommend to me. And then also we want to recruit external partners to be a part of Activate. So getting your advice on that would be wonderful. And that's the end of my part. This is at least part of our team who attended our first science team meeting. This is in front of the Falcon in the NASA Langley hangar.